Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania na watu wake. Ibariki Tanzania, ibariki Tanzania, tubariki watoto wa Tanzania.
How are you, everybody who is watching this fantastic video? I would like to take this opportunity to welcome you into this fantastic moment. My name is Olenjolain, Mokota Yellow Single. Simply you can call me Olenjolai. I'll be your advanced physics teacher in this program. I thank God by His own grace that He has given me a chance to teach local students, national and international students. In this teaching, throughout of this teaching, I'll be using the syllabus of United Republic of Tanzania that's called the Physics Syllabus for Advanced Secondary Education, Form 5 through Form 6, which has been prepared by Tanzania Institute of Education, or shortly we call it TAI. I am a Tanzanian, and this is our national flag. I'll be using the syllabus of our beautiful country. However, that for the international students, we take advantage because the advanced physics we are going to cover is cross-cutting. So it means that what we are learning right now in Tanzania, in advanced physics in our country, in our beautiful country of Tanzania, is what other students are learning in India, in Indonesia, in Asia, in United States of America, and even some other places, including the United Kingdom, which actually is our colony. And hopefully that even in Germany, these are the stuff that advanced students used to learn. So I ask you to join me, and you should be focused, you should be serious. I would like just to remind you quickly about the vision that we have in this online school. This is the vision that we have. We have an assignment to teach and train advanced secondary students on how to extract the knowledge, understanding, and wisdom from the classroom instructions and combine it with knowledge, understanding, and wisdom that will teach them to extract it from the Word of God in order to solve real-life problems. The main objective of TOASO is to teach our students on how to solve real-life problems, because that's the main objective of any educational system, including our educational system. So we have specific objectives, and some of the specific objectives, for example, will be preparing our students to perform well in the year continuous assessment, to understand every subject and love it, because that will be one of our target, to make all our students to love advanced physics, advanced chemistry, advanced mathematics, and even also basic applied mathematics. Before even I go and explain to you briefly about what I've written to the blackboard, I would like also to invite you to interact with me through questions, through comments, through feedback, through testimonies, through anything else that you want to share with me, through just your acceptance of the contents that we are going to teach you, through the comment sections. Interact with me through the comment sections. With any comment that you write, I will see, and I'll try my level best to act on it. Or even some other students worldwide or in the entire country of Tanzania will see your comment and answer your questions as well as they can. So let us interact there in order to make sure that we build each other, and even also we address the concept that you have been troubling around too. So right now, I would like to take this opportunity to welcome all our advanced secondary students into Tanzania Online Advanced Secondary School in Olenjolain. Simultaneously, I would like to welcome all our viewers into our official YouTube channel that called Tanzania Online A-Level Secondary School in Olenjolain. So we have more than 3 departments in our TOASO school. The first department is called Advanced Physics, where we are teaching 2 subjects, Advanced Physics for the Form 5 and Advanced Physics for the Form 6. The subject of the day is Advanced Physics. The main topic is called the Electromagnetism. And these contents we dedicate them to pre-Form 6 students, or Form 6 students, or visitors, or QT students, or grade 12 students, and teachers of all these levels even including physicists who love to enjoy the beauty of advanced physics. We have 3 chapters in the main topic of electromagnetism, and the first chapter is called Magnetic Fields and Forces. This is session 2. We are done in session 0, session 1, and this session 2 is titled as Magnetic Fields on a Currently Carrying Conductor. That's what we'll be focusing on that. However, that also will be discussing about Georgie. We'll be discussing about the force which will be acting on the conductor that is being placed in the magnetic field. Okay, so let us go into the quick review. Let us start. Take your pen, have a fresh mind. Let us start with quick review of session 1. So basically session 1 is being entitled as terminologies of 40 terminologies of electromagnetism. Terminologies of electromagnetism. Terminology of electromagnetism. In this terminology of electromagnetism, we have learned 8. I've taught you 8 terminologies of electromagnetism. The first one is called the magnetic pole. The second terminology is called the magnet. Okay. Then the other ones we learned about another terminology called the magnetic field. Then the other terminology called the magnetic field line. Okay, magnetic field line. Then the other terminology is called the magnetic materials. Magnetic materials. Then another terminology we told you about non-magnetic materials. So 1, 2, 3, 4, 5, 6. Then the 8th terminology we told you about magnetic flux. Magnetic flux, which is psi. Then the last terminology we talked about magnetic flux density. So magnetic flux density, which is capital B. So these are 8 terminologies that we have covered in session 1 in detail. And especially these 2 new terminologies, I've taught them in detail, and I've given you the mathematical definition there. Just I've given you more than one definition so that you can have choices. So we have discussed this so many information. In case you missed it, you should not worry. It is still in our official YouTube channel that called TANZANIA Online, A-level second school in square bracket in OLENJOLAI. So today we'll be focusing on the magnetic fields. Magnetic fields of the currently carrying conductor. So let us focus on magnetic field on the current carrying conductor. And let us start with history. When did this subject has been discovered? In 1820, a physicist called Oersted discovered a wire carrying an electric current. A wire carrying an electric current has associated magnetic field. A as associated magnetic fields. There's associated magnetic fields. So this physicist has did some experiments and discovered that a wire carrying electric current has associated magnetic fields. And then he did his experiments with the following conductors. So the current carrying conductors can be any of these three types. The first one, it can be a straight wire, so we got a straight wire conductor. It can be solenoid conductor. It can be a circular wire conductor. So the current carrying conductors may be either of these three conductors. Maybe of these three conductors, a circular wire conductor, or it can be a solenoid or a straight wire conductor. So simply in a wire current carrying conductor, the associated magnetic fields. The direction of this the directions of these fields is determined, maybe the direction of these fields may be determined by the following rules. May be determined by the first rule, that we call it right-hand grip rule. Right hand, we learned this in O level, right hand grip rule. Right hand gripping rule. Right hand gripping rule, or right hand grip rule. Gripping rule. Right hand grip rule, gripping rule, right hand gripping rule, right hand gripping rule. So we have a fundamental question here. State the right hand grip rule. I don't think it has any grip rule. So we say the right hand hand grip rule state that imagine you are holding a current carrying conductor with his right hand with the thumb pointing to the direction of electric current pointing the directions of electric current and the other gripping fingers point the direction of magnetic field. This is how the right hand grip rule state. The right hand grip rule state that imagine you are holding a current carrying conductor with right hand with the thumb pointing the directions of electric current and the other gripping fingers pointing the direction of what magnetic fields. Remember that I'm teaching you the rules, two rules, which we use in physics to determine directions of magnetic field. What does it mean? Suppose that this is the current carrying conductor. It's a straight wire, or it is, yes, it is a straight wire conductor, a straight conductor. Right?
Yes.
So it's conducting electricity maybe from point A to point B. So this is your right hand. And then you are holding this conductor in this way. For instance, suppose that this is your conductor. Like this. This is your conductor. And then the electric current is flowing in this direction. So when you say that you have to hold this straight conductor in such a way your thumb point the directions of what? Point the directions of
Electric current.
electric current, which we call conventional current. These gripping fingers, where are the gripping fingers? These are the gripping fingers. These are the gripping fingers. So these gripping fingers point the directions of magnetic field. So what does it mean? So when electric current is flowing in this direction, then the magnetic field lines surrounding the current carrying conductor. Because according to Olenjolain, he said that Olenjolain discovered a wire carrying electric conductor has associated magnetic fields. So because remember electromagnetism, we say that is a process of producing magnetism due to the flow of electric current in a conductor, right? So suppose this is the conductor, the current is flowing in this direction. If you grip in this way, then you find that the magnetic fields surrounding around what this straight wire conductor. Are we together?
Yes.
Yeah, so mean that when this is a straight conductor, if you apply the gripping right hand rule, so we have the surrounding magnetic fields. So you have surrounding magnetic field like this. So because you're holding this way, so the directions will be pointed by the gripping fingers. So these are the directions of 40 magnetic field lines. So these are the directions of 40 of magnetic field lines. So, and this is the direction of what? Of magnetic field, direction of magnetic field lines, which you are dealing with. Magnetic field lines, which are imaginary lines surrounding the straight wire conductor. So this is what current carrying conductor. Current carrying conductor. And this is the direction of 40, direction of conventional current. Conventional current. So this is figure 2.1. So demonstrations of 40, the right hand grip rule. The first rule. The second rule, it has been stated by Maxwell, the great physicist who did so many experiments and he contributed a mathematical questions which we call Maxwell questions, which is all about it, magnetism and electricity. So the second rule is called the Maxwell corkscrew. Maxwell corkscrew. Maxwell corkscrew. So this was the first question. This is the second question. State Maxwell's corkscrew rule. Maxwell corkscrew rule straight up. Imagine driving a screw in the direction of conventional current. Conventional current, we mean direct current conventional current and the screws and the rotation and the direction and the rotation of and the direction of rotation So imagine driving a screw in the directions of the conventional current and the directions of rotation of the screw and directions of the rotations of the screw show the directions of the magnetic field. Shows the direction of the magnetic fields. So, the Maxwell-Cox-screw rule states that imagine driving a screw in the directions of the conventional current and directions of rotations of the screw shows the directions of what? Directions of the magnetic fields. What does it mean? Suppose that this is the screw, and then possibly here we have a place that we put a flat screwdriver, and then this screw has the screws, or something called in physics is thread. So these are the thread. So it means that, for example, if you're driving this screw, this is the directions of what? This is the directions of conventional current. So it means that this is the directions of what? Of currents. And then this is rates means if you are, so you see, for example, if you are spinning it, for example, this will be rotation. So these rotations of the straight means this is rates. This one will show the directions of what? Magnetic fields. Magnetic fields. Okay? So when the screw, it means the screw is going maybe downwards. For example, that if you are, for example, the screw is going downwards or is driven downward, so suppose the directions of current is going downward, right? So the threads now that will be rotating and getting into the female part is what representing what? The directions of magnetic field lines. So this is figure 2.2, and this is called the Maxwell cork screw rule. Okay, so it means that, so now you can say that by using these two rules, we can show the direction of the magnetic fields due to current carrying conductor, due to current carrying conductor. Okay. So let us start with the first shape of this conductor, which is straight. So it's a magnetic field direction of directions of magnetic field directions of magnetic fields in a straight conductor. In a straight conductor. In a straight conductor. So directions of magnetic fields in a straight conductor. So the direction of magnetic field due to directions of magnetic fields due to current flowing in a straight conductor can be shown by a right hand grip rule. By a right hand grip rule. So can have a flow, we can have two different conductors, but electric current is flowing in the opposite direction. So this is supposed to is conductor A and this is conductor B. So stop right. So by using the right-handed grip rule, if we grip this conductor in this way, then we say that the thumb will point directions of what? Conventional current. And the gripping fingers point directions of what? Magnetic fields. So here we are going to have magnetic fields surrounding this conductor. We have magnetic fields surrounding this conductor. We have magnetic fields surrounding this conductor. I have magnetic fields surrounding this conductor. We have magnetic fields surrounding this conductor. What the direction? The direction of gripped fingers. So in this way. Also, for this one, you have to grip it in the opposite direction. It's the right hand, don't use the left hand. So then we'll have also magnetic field surrounding this straight wire conductor. So these are the magnetic field surrounding the straight wire conductor. Straight wire conductor. So the directions will be opposite. So on this side is the directions of the fields. Then the second conductor, we said it is what? Solenoid. Direction. Directions of magnetic fields. Magnetic fields. In a straight conductor.
A straight already.
In a solenoid. So directions of magnetic fields in a long solenoid. The direction of magnetic fields in a solenoid is determined by the right hand grip rule. How we use this? So say grip at the top of the solenoid. So grip at the top of the solenoid in such a way that the sun point, the direction of electric current directions of electric current. So grip at the top of the solenoid in such a way that the sun point the directions of electric current, and the as a gripping fingers point the direction of magnetic fields. Do you remember the shape of the solenoid? Or you have never seen it? You have seen the solenoid. Have you seen it physically?
The shape?
The physical solenoid. So we have a cylindrical conductor. So if this is the switch and this is separator, so you can call it what? Hello? So it means that if you close this switch, the current will be flowing in this direction, the directions of conventional current. So current will be flowing in this direction around this cylindrical conductor. Okay?
Yes.
So when current flowing through this cylindrical conductor, because it's the way that it's operating, it's the way that we use to formulate solenoid. Solenoid is nothing, just having a cylindrical conductor which has some number of turns. Okay, some number of turns. So this is what we call them turns. For example, you can count 1, 2, 3, 4, 5, 6, 7, 8. Let's say, okay, so let's say 7 turns. So you have 7 turns. And this solenoid is actual word to use to form even a transformer. So you used to hear that a transformer is a certain number of turns. So that turns means that the number of looped wires or looped wire. Okay? So it means that this is the source of electric current that will be revolving around that cylindrical conductor. And when it's revolved, then you can find that this side where electric current get in is a cylindrical conductor becoming the south pole of the magnet because there is a production of magnetic fields, and this one will be becoming the north pole of the magnet. So when the point where current enter becomes the south pole, and the point where current leaves becomes the north pole. Right?
Yes.
So for that case, now, because there is a flow of electric current, then experiments show that there is also magnetic fields inside this conductor. So these are the magnetic field lines. They are passing inside the conductor, like this. So these are the magnetic field lines. But I told you that this is south, this is north. So it means that the magnetic field lines always will be moving from north pole to south pole. Okay?
Yeah. So
means that these magnetic field lines are inside of this cylindrical conductor. So they are still just in these three regions, because yesterday I told you about magnetic field lines, I talked about magnetic field regions. So you've covered a lot of stuff concerning about this. So here also we have magnetic field lines. So this is north. Then again we have another magnetic field lines. Then again we have another magnetic field lines. Then we have another magnetic field lines. Then we have another magnetic field lines. And we have another magnetic field lines. So this is figure, I forgot this one, this was figure 2.3. So it's all about straight conductor. Figure 2.4, this is all about magnetic fields on a solenoid. So those are the magnetic field lines, and that's how we used to apply a gripping right hand rule. So you see, for example, you see,
yes.
Look here. These are the directions of electric current, right? Then grippy fingers indicate the directions of what? Magnetic fields. These magnetic fields, they don't only pass in this way, they also, for example, this is the cylindrical conductor. Also magnetic fields pass in this way, but because this is two-dimensional blackboard, we don't have three-dimensional blackboards. So we just represent these lines are just they are passing at the top. But remember, I told you, if these are the directions of current, these gripping fingers are the direction of magnetic field lines. So you see that even the directions is from this side to this side, right? If you reverse the directions of current, for example, if you change the positive pole and negative poles, or positive terminal and negative terminal, then even the directions of magnetic field will change. Are we together?
Yes.
So if the direction of magnetic field should be It means that in this way, direction of conventional currents will be changed. Even directions of magnetic fields also will be changed. Okay? Yeah. So you have to understand the facts that we are talking about. Then we have another structure of current carrying conductor, which you have mentioned, and this we call it what? Circular coil. So let us finish this directions of magnetic field lines on the circular coil, then we'll go on another concept that we call it force on a conductor of current carrying conductor. So to label, these are magnetic field, and this one is solenoid. These are turns. And this is current carrying conductor. This is a switch. This is battery. Etc. Okay, so let us see direction of magnetic field in circular coil. Circular coil. The direction the directions of magnetic field due to current flowing in a circular coil is determined by Maxwell corkscrew rule. Suppose that we have this conductor. Okay, so this is just a shape where we place this circular coin, and in this shape we have two holes. The first hole means that we can drill a hole here, and then here we have another hole to form a circular coil. So look, so here we have what? We have some wires hooked together. So we are formulating a circular coil. So suppose that all of these are conductors, but you are formulating a circular coil. This is flow of conventional current. And then this is a physical structure, for example, a table, right? And this is a circular coil. So listen. So it means that now the right-hand gripping rule or the corkscrew rule, suppose that you are driving now the corkscrew rule in this direction. So it means that the directions where it's being driven, it indicates directions of what? Conventional current, right? And then directions of the straight will be what? Indicating the directions of what? Of magnetic field. For instance, at this point, so you see that the magnetic field lines are this way. So these are the kinds of the holes, but okay, so you can just draw them as magnetic field lines. So if you start on this side, you will find that the magnetic field lines will be in this direction. The directions of magnetic field lines. Again, these directions of another magnetic field lines. And then these directions of another magnetic field lines. Etc. So on this side will be what? Will be opposite. So directions of magnetic field lines, direction of magnetic field lines. electromagnetic field lines, and electromagnetic field lines. So these are magnetic fields. Also these are magnetic fields. And this is circular coil. And this is figure 3, figure 2.25. Circular coil. Magnetic fields of circular coil. Okay, so that the figure or that the presentations of what of magnetic field lines or magnetic fields, directions of magnetic fields due to the current carrying conductor. So then the next concept now, let me teach you about force acting. Just to say that force acting on a conductor, on current carrying conductor, force acting on a current carrying conductor. Placed in magnetic fields. So force acting on a current carrying conductor placed in magnetic field. So he said that when a current carrying conductor is placed in the magnetic fields, then it experiences force. Experiences what? Experiences force So when a current carrying conductor is placed in magnetic field, then it experiences force due to magnetic due to fields. What does it mean? For example, you know that if you have two bars of magnet, this is north, and then you have another bar of magnet, which is opposite pole, and this is south pole. So we say that unlike poles of magnet attract each other, right? So if attract each other, it means that always the north pole will be giving outward magnetic fields. The north poles will be giving out the magnetic fields, the south pole. The north poles giving magnetic fields, the south pole. The north poles giving magnetic fields, the south pole. The north pole giving magnetic fields, the south pole. The north pole giving magnetic fields, the south pole. North pole giving magnetic fields, the south pole. So we know that we have a magnet. This is figure 4.6. So there we have two bars of magnets, and this is a regions of magnetic fields. Okay? In these regions of magnetic fields, we have magnetic field lines here. What happens if we introduce a current carrying conductor there? That is the first case. So this is the first case. This one. So we want to think about case 2. So what will happen to the current carrying conductor that placed in that magnetic fields? So this we call the magnetic field region, or regions of what? Magnetic fields. So this is north, this is south. So this is case 2, because I think that we need more space. If the current carrying conductor is placed in the magnetic field, then so here we have the regions of magnetic fields. these are the two bars of magnet. And then now, let's introduce the straight wire conductor. You can also introduce a solenoid, but in most cases, we introduce a straight wire conductor. You have to stop writing, listen carefully. And suppose the directions of the current in this straight wire conductor is, let's say, from point A to point B. So it's flowing from bottom to top on this blackboard, right?
Yes.
So then here we have magnetic fields due to the magnet. So this is a magnet, and this is also a magnet. This is not a current carrying conductor. So this is also what? This is magnet, and this is magnet. Okay? So if you grip on right-hand rules, what do you expect? Because this is a current carrying conductor. So we say whenever we have electricity, there is a magnetism. Whenever we have electric fields, we have magnetic fields. And whenever we have magnetism, we have electricity. So it means that this is the current carrying conductor itself. As itself, we have studied it by using the right-hand grip rule and cork rule, Maxwell cork rule screw, Maxwell cork screw rule. We have realized that whenever we have a flow of electric current, we have magnetic fields, right?
Yes.
So if that's the case, suppose that we don't have magnetic fields, we just have only this current carrying conductor. Where will be the directions of fields? So the directions of magnetic fields will be in these directions, okay? So we have here magnetic fields due to a current carrying conductor. We have another imaginary lines of magnetic field lines. We have another imaginary lines of magnetic field lines. We have another imaginary lines of the magnetic field lines. We have another magnetic field lines, imaginary magnetic field lines. Okay? So we have this way, and then where the directions of them? This way, this way, this way, this way, this way, right? And here on this side, on this side, on this side, on this side, on this side. So what do you find? Look here. So the magnetic field lines due to magnet at this point are flowing in this direction, right? So the magnetic field lines, for example, suppose that this is point C and this is point D. Listen carefully. So at point D here, or at point C, magnetic field lines flow in this direction, right? Due to the magnet. Magnetic field lines due to the magnet flowing from north to south. Okay? While magnetic field lines due to the current carrying conductor flowing from this side to this side. So they are flowing in opposite direction. Right? Right?
Yeah.
So magnetic field lines due to the current carrying conductor flowing in opposite direction to the the directions of magnetic field lines due to the magnet. Are we together?
Yeah.
So because they do flow in the opposite direction, something is going to happen, which I will tell you soon. Then at point D, magnetic field lines flowing from North Pole to South Pole, right? So they are flowing in this direction, isn't it? Huh? Magnetic field lines do the two bars of magnets, they are flowing in this direction, right? Then magnetic field lines on these sides, let's say, the magnetic field lines, whether on this side or this side of the conductor, magnetic field lines, due to the current carrying conductor, are also moving in the same direction, right? So you can say that this magnetic field lines due to the magnet, and this magnetic field lines due to the current carrying conductor. And these are magnetic field lines due to the magnet, and these are magnetic field lines due to the current carrying conductor. So we remember the principle that we introduced to you for the first time in wave. We call this superposition principle in wave, or in electrostatic we talked about superposition principle. So in superposition principle we say that when you have two vector quantities which are in same directions, we sample, right? And if they're in opposite directions, they cancel each other. Okay? So at this point, all of these are magnetic fields. This is magnetic fields, and this is magnetic fields, right? Suppose that they have the same magnitude. So at this point, at point C, the magnetic field lines due to the magnet will cancel with magnetic field lines due to the current carrying conductor. Are we together? While at 20D, because the magnetic field lines due to the magnet and magnetic field lines due to the current carrying conductor are flowing the same direction, so they reinforce each other. So we have a strong magnetic field on this side rather than at the bottoms of these diagrams compared to the magnetic field lines at the top. Are we together? So what will happen? So on this side, at 20D, we have strong magnetic force compared to at the top. We have weak magnetic force. So this conductor will always be pushed up. And because it will be pushed up, so it can make this conductor to experience some kinds of the motion. And that motion there's no anybody else but itself experience some kinds of motion because this one will be pushing it up. So at 20D, so here we have what? Strong what? Magnetic fields. And at this point we have what? Weak magnetic fields. Okay, so this is figured 2.7. What should you write here? Force acting on what? On a current carrying conductor, press the magnetic field. If you have any question, don't hesitate to ask me for the local students who are in this class. And if you are online students, you have any question about that force, which will be acting on the current carrying conductor, don't hesitate to ask me in the comment section of this session. So we say from figure 2.7 above, the resultant magnetic field is strong at D due to reinforcement of what? Due to reinforcements of magnetic fields. Reinforcements of magnetic fields. So the current carrying conductor, is moved from D to C. Why? Because at sea we have weak magnetic fields. If that's the case, then we can come into the concept now which we've been seeking, or which I gave you the homework in previous session, which is, okay, so now we have seen whenever we place a current carrying conducting magnetic fields, it experiences what? A force. And this is called magnetic force. Called magnetic force. So, how about force is a vector quantity. Force is a vector quantity. So it has both magnitude and the direction. It has both magnitude and the direction. So now, let us name the concepts of direction of force due to magnetic field. Directions of force due to magnetic force. So direction of force. So you say the directions of force of a current carrying the direction of force acting on a current carrying conductor. The directions of the force acting on a current carrying conductor placed in magnetic field is determined by Fleming's right handy. Fleming right handy, which I gave you as homework 1 in previous session. So because I have some local students which they need this question, and the questions was stating that state Fleming right handed.
Fleming left hand.
Fleming left. Oh, excuse me. Fleming lefty hand rules. So you hear them, they are correcting me. Fleming's lefty handy rule. We have a question here. State the Fleming lefty hand rule. So in order to participate with students in this session, because I gave you this homework, I would like to quote one of the Fleming's lefty hand rule, which has been found by at least the one students. I think all of them, they found the same response and they are right and they got it. And let me just prefer one of them to read on your behalf. You're sure? Okay. State your Fleming left hand rule.
Fleming left hand rule state that if you hold,
wait a moment, state that if
you hold
you hold
a current carrying conductor,
if you hold a current carrying
conductor by your left hand,
by your left hand.
in your left hand,
Mine say that if the first finger say, okay, there are different way of saying, but to each other, such that the first finger held mutual or at right angles of the left hands. So if you are holding a current carrying conductor on by your left hand,
it is on.
now you are changing.
Yes.
I'm not sure about your statement. On your left hand,
Yes.
did you compose yourself?
No.
And
the thumb,
if you hold a current carrying conductor on your left hand,
and the thumb,
uh,
first and second finger in right angle to each other. Then the thumb will point the direction.
and the thumb. If you hold a current carrying conductor on your left hand, such that
the thumb, first finger,
the first finger, and the second finger are
in right angle,
healthy or out,
mutually.
are healthy mutually at right angles. Are healthy mutual at right angle. At right angles.
Then the thumb
And the thumb
will point the direction
point
the direction of the force.
Directions of what? The thumb point directions of the force.
Yes.
The first finger
Direction, point the direction of the magnetic field.
point the directions of what?
Magnetic field.
Magnetic
Field.
of magnetic fields.
And the second finger
And the second finger,
will point the direction of the convection current.
second finger point the direction of
The convection current.
conventional current at the end of your stating.
Yes.
Okay. So we say that these are the three fingers of the left hand. So if these three fingers are held mutual at right angles, so we have a right angle. We have a right angle between this finger and this finger. And we have a right angle between this finger and this finger. And they have a right angle between this finger and this finger. We have three fingers, so that these three fingers should be held in such a way that they are forming three right angles. Right? So afterward, when you're heading this one now, the first finger will be pointing directions of 40. The first finger point directions of 40.
The thumb first.
Yeah, the second finger now, this one. This is the thumb, first finger, second finger. So the second finger point directions of current. Okay? And then the thumb point directions of 40, point directions of the force. And the first finger point directions of magnetic field. So in summary, thumb show the directions of 40 of direction of force. Then I have first finger. Point directions of 40. First finger point directions of 40, magnetic field. Then I have the second finger. Point directions of 40. Directions of current. So the Fleming's left hand rule is only shows direction. It does not show magnitude. It shows directions of magnetic force or magnetic fields, and shows directions of directions of magnetic fields, show the directions of the force that will be pushing up the current carrying conductor, and also it shows directions of current or conventional current, the actual current that flows through the conductor. Right?
Yes.
That's all about Totti, Fleming left-handed rule. So from this fact now, we can deduce 4 factors which are affecting the magnitude of the force. The magnitude of the force. So yesterday it was example 1. This is example 2. This example 2 refer advanced certificate secondary education examination of 2019, paper 2, question 9. Roman 1. Question 9a, Roman 1. And the question say that identify, I'm about to end this session, identify 4 factors that affect the force experienced Identify 4 factors that affect the force experienced by a current carrying conductor. So the question says that identify 4 factors that affect the force experienced by a current carrying conductor. Experienced by a current carrying conductor. Mind 4 factors that affect the force experienced by a current carrying conductor in magnetic field. By current carrying conductor in So this is it. So you might imagine in session 2, we are starting answering some questions in next exam. Just the long terms of this of ACSEE, it's Advanced Certificate Secondary Education Examination. So identify 4 factors that affect the force experienced by a current carrying conductor in magnetic field. In magnetic field. In magnetic field. So determine those 4 factors. Solution. So the first step to answer these questions, and password is going to give us 4 factors. So solution: factors affecting the force in the conductor. So solution. So you say that that's all about factors. Okay. So the subtitle of this part is called the factors factors that affected the force experienced by a current carrying conductor in magnetic field. So the first step, say sketch the problem. Sketch the problem. So suppose that these are the magnetic fields. Suppose that these are magnetic fields. These are magnetic field lines. Magnetic fields. So this magnetic fields, this is current carrying conductor. And here we have an angle theta. So it can also form an angle theta here, and also form an angle theta here, etc., etc., etc. So there are 4 factors which can affect the magnitude of the force of the current carrying conductor placed in the magnetic field. So second step, say the first factor is length of the conductor. So length of what? First factor is length of the conductor. How does length of conductor affect the magnitude of the force experienced by the current carrying conductor? This is the rule that the magnitude of the force experienced by the current carrying conductor placed in the magnetic field is directly proportional to the length of the conductor. That's the first factor. The third step. So we say the second factor is magnitude of of electric current, because here we have flow of electric current also. When you say length of the conductor, is the length of the conductor. Hence, you have the flow of electric current. So say magnitude of 40, magnitude of electric current, magnitude of electric current, which is R. So we say the magnitude of the force is very proportional to the electric current. Okay, proportion of the electric current. Again, the force is the semi factor is magnitude of magnetic flux density. Magnitude of magnetic flux density. How does magnitude of the force acting on the current carrying conductor plus magnetic field relate to its magnitude of the magnetic flux density? We say that the magnitude of force is very proportional to the magnetic flux density. So this is the fifth system, but it's a force factor. Force factor, we say that is sine of the angle between the current carrying conductor, in the current carrying conductor and the magnetic field or cosine of the angle between normal of conductor and the magnetic fields. So it can be either cosine of the normal of the conductor, not cosine of the angle, or it can be sine of the angle. But if it's sine of the angle, you have to consider the angle between what? Conductor and magnetic field. If you are focusing on the cosine, or if you know the angle between the normal of the conductor and magnetic fields, then you have to use cosine. So mean that also the relationship between the magnitude of the force and the sine of the angle is very proportional. So magnitude of force is very proportional to the sine of 40 of the angle theta. Should be dealing with that. So this is theta is the angle. Listen, theta is the angle between what? Magnetic field and conductor.
Yes.
What the normal of the conductor. For example, if you are considering the normal of this conductor, you might find that it's somewhere else there. So it's a straight line. Normal line. You know normal line. For example, the normal line for this blackboard is here. The normal line for this ruler is here. Right? So similarly, the normal line for this conductor provisionally might be here. So you see that also it makes a certain angle with this magnetic field. Suppose this angle to be alpha. Even here it makes an angle alpha. Okay?
Yes.
At the normal. So this is what? This is normal. For example, if this is the ruler, you want to determine it's normal, right? This is normal. Okay? Okay. This is 30, it's normal. If you put it this way, this is normal. Are we together?
Yes.
Yeah, so normal the conductor. So also, if you consider the normal, the angle between the normal of the conductor and magnetic field, also the relationship is direct proportional. So this is direct proportional to the cosine of 40 of alpha. Okay?
Yes.
So mathematically now, the four factors that affect the magnitude of the force. The first one, so we say force is direct proportional to the length, direct proportional to what? To the magnitude of the current, is direct proportional to the magnetic flux density, is direct proportional to the sine of angle theta. Right? Then we say that the magnitude of force is equal to length times current times magnetic flux density times sine of angle theta. Here we used to have K, but K is equal to proportional to constant is 1. So simply say that force is equal to magnetic flux density then times length of current carrying conductor, then have sine of angle theta like this. So this is very important formula that's used to compute magnetic force acting on what? On a current carrying conductor, where theta is angle between what? Conductor and the magnetic field. L stands for what? Length of the conductor. I stand for what? Current of what? Current flowing through the current carrying conductor. B stands for what? Magnetic flux density of what? Of the magnetic field. Then we say that if, for this case, angle theta is 90, this is right angle, right?
Yes.
So sine of 90 is 1. So it means that the magnitude of the force for this case is equal to BR sine of 90, which is equal to 1. So magnitude of force is equal to magnetic flux density times current times length. This is the formula of magnitude of force, which in short we call it BI. So many students, they just remember this formula by just recalling BI. You know BI? BI is a common word used, however it's missing one error, but it's a common word used in parliamentary place. BI, mswada. So if you add the L, it means you get mswada. So we are giving students some few tricks for them to remember the formula. If there's a formulations, or if the angle between the normal of the conductor and magnetic fields is given, then we say that the magnitude of force is then proportional to the magnetic flux density, then proportional to the current, then proportional to the length, then proportional to the cosine of angle alpha. So if we eliminate this proportionality constant with K times magnetic flux density times current times length times cosine of angle alpha. So but K is equal to 1. So force is equal to magnetic flux density times electric current times length times cosine of angle alpha. So this is another formula that we need to know in mathematics. If you have understood, then now do this homework 3, homework 2. Simple question. A long straight conductor. I know now students are happy because they hate the homework. They're not happy because of the homework, they hate that we are approaching to the end of the session. So a long straight conductor or wire carrying current of 6 ampere lies at right angle lies at right angles to the magnetic field of 2.5 Tesla. Find the force current length of the wire. So that's the homework. A long straight conductor or wire carrying a current of 6 ampere lies at right angle to the magnetic field of 2.5 Tesla. Find the force per unit length of the wire. So if you do this homework, make sure that you submit in the comment sections, and I would like to say that this is the end of session 2, which is titled as Working Magnetic Fields on a Current Carrying Conductor. And I would like to invite you in the next session where we'll be learning about the motions of the charged particle in magnetic fields, and then we'll be having some problem solving in relations to the formula that we've been deriving. So stay tuned until we meet in the next session, which is session 3. You should not miss it because it's around the corner. And you have to make sure that in case you feel from your heart you want to offer our living God your free thanksgiving of any amount in order to support the running cost for this week, don't hesitate to send your free thanksgiving through the telephone number 0759745331, and may God bless you abundantly according to the scripture that I've written there. Those are the scriptures that will help you to receive the blessing. But again, I would like just to have just to present to you another announcement. We do have also a TANZANIA Online Advanced Library. So we call it TANZANIA Online Advanced Library. You can access different books. For example, this book is called the Physics Syllabus for Advanced Secondary Education from 5 and from 6. Again, this is it's a book called the Principles of Physics. We have Principles of Physics 1 or S-Chan 1 and the Principle of Physics 2 or S-Chan 2. You can also order this reference textbook. Again, we have reviews, we have questions and answers books. This is called Advanced Physics 1 Review, questions and answers from 2003, 2016. And this is Advanced Physics 2 Reviews, questions and solutions of 2006 to 2020. So you can order. We have actually the affordable price. How can you order these books? That's a very good question. Just send it an SMS of your order through this telephone number, and then we'll make a call. We'll call you and then just negotiate. Not just there's no kind of negotiate. Then we'll give you more information on how you can order and receive your package. We really advise from 60 students or from 5 students to have this package of books for them to dig and even to go far from what we are teaching them, because these are the reference books that we are using, and we like to equip them so that they can learn themselves and master the beauty of advanced physics. So to place your order, just place your order, send an SMS, and then remember that we can ship these books in any regions of United Republic of Tanzania. Whether you're in Ruvuma, we can ship these books to you. Whether you are studying in Kagera, we can ship these books to you. Whether you are studying in Sumbawanga, we can ship these books to you. So you should not be in fear. The only thing is you have to follow some few instructions that we will give you when we'll be having a phone call with you. You are warmly welcome in Tanzania Online Advanced Secondary School to enjoy the beauty of advanced physics, advanced chemistry, advanced mathematics, and basic applied mathematics. So because we had an opening prayer, or maybe even if we didn't have an opening prayer, but we like to have a thanksgiving prayer to God, who have taught us so many concepts today. God has taught us about a grip right hand rule. Then he has taught us about Maxwell corkscrew rule. He has taught us about Fleming left hand rule. He has taught about straight conductor. He has taught about solid circular coil. He has taught about the magnitude of the force acting on the carrying conductor that places the magnetic field. Then finally, he has taught us about these formulas, which we'll be using them consistently in the future session. So let us give God thanks for the great thing that he has done in us. Our Father who is in heaven, we come before your presence as your children. We surrender and give you all the glory and honor for everything that you have done in this session 2 of the magnetic fields to the current carrying conductor, Father. We thank you for the great thing that you have done. We thank you because you have opened the mind of the students who are watching these programs anywhere, at any time of the present and future generations. Father, thank you for your blessing. You have opened their mind to comprehend and apply these informations for the rest of their life. Father, this is all about the beauty of electromagnetism. We give you the glory and we invite you in the next session, which will be session 3. Do your own preparations. Prepare me as your child and as your donkey, Father. And also prepare your children to receive the good news that you have prepared for them. In Jesus' name, amen.
Amen.
So, my dear student, may God bless you. And this is Tanzania. And this is our beautiful country. We love you so much. Keep enjoying the beauty of advanced chemistry. And